Hello, I'm glad you're here. Maybe you're lying back with the lights low. Maybe the day has quieted down. Maybe you've just found a moment where everything feels still. However you arrived, I've made this place for you. A place without rush. A place where thinking can be as soft as breathing, and questions can rise and drift like clouds. If you're already enjoying this quiet moment, I'd love it if you gave the video a gentle like. Maybe even subscribe if you'd like more of these slow science wanderings. And if you're listening from somewhere special, a cabin in the woods, a small town by the sea, or just your favorite blanket in your favorite chair, feel free to leave a comment and tell me where. I always love seeing the bedtime map slowly light up, one quiet mind at a time. Tonight, let's let one question carry us. Not loudly, not urgently, just quietly, like a thought turning slowly in your mind. Does time exist without the universe? It sounds simple at first. You've said the word time a million times. You've checked clocks, counted hours, remembered birthdays, waited for moments to pass. But somewhere under all those seconds and minutes is a deeper question, one that asks not what time does, but what it is, and more than that, whether it can be there when nothing else is. To begin, it helps to just notice time, not in theory. Just as you feel it now, you're listening to this voice. One word follows another. That's time. There was the moment you pressed play. There's this one now, and there's the one that's coming next, all different, all ordered, all flowing forward in a way that feels natural. You might not even notice it unless something interrupts it. A long pause, a sudden silence, a skipped beat in the rhythm of the world. Then suddenly you feel time again, or the absence of it. But what is it? You're not holding anything when you say a minute has passed. You're noticing change, a change in sound, in your thoughts, in the air around you. Time seems tied to that, to motion, to transformation. If nothing changed, would time still be passing? Think about the room you're in, the way your body feels as you lie or sit. Your breath moves in and out. Maybe a clock ticks somewhere. Maybe light shift across the wall. You know you're in the present moment, but you also know that the present used to be the future, and that, in just a second, it will become the past. Everything seems to lean in one direction. This is where our journey begins, not with answers, but with attention. What you're feeling right now is how time makes itself known. It doesn't announce itself, but it structures everything, not just your schedule or your memories, but the basic fact that anything happens at all. Now imagine removing that structure. Imagine no ticking, no motion, no before or after. Would anything remain? That's what we'll explore slowly and carefully. Let's step outside the ordinary just a little, back up from the clocks and calendars and phone reminders. Look not at how we measure time, but at how it works under the surface. You've probably heard the phrase, time is an illusion. It's said a lot in science circles, sometimes in philosophy, sometimes even in fiction. It doesn't mean that everything you feel about time is wrong. It just means that time might not be as fundamental as it feels. You can think of time as something woven into the universe, not just something that exists within it, but something the universe creates as it goes. Kind of like how music only exists because notes happen one after another. If you had just one note and it never changed, would there be a song? Physicists have looked at this closely. When Einstein introduced his theory of general relativity, he changed how we think about time completely. In his view, time and space aren't separate. They're part of one fabric, one geometry, what we call space-time. Mass bends this fabric. Planets, stars, you, me, everything with mass tells space-time how to curve, and curved space-time tells everything how to move. It's strange to think about, but it means time isn't the same everywhere. The closer you are to something massive like Earth or a black hole, the slower time moves for you compared to someone further away. This isn't just theory, it's measurable, it's real. Even the GPS in your phone works because satellites correct for this time difference every moment, automatically. Otherwise, your location would drift by kilometers every day, so time is relative. But here's where the deeper question sneaks in. If time depends on the structure of space-time, then does it make sense to ask what time is without a universe? If the fabric doesn't exist, what's left for time to live on? It gets even more puzzling when you go back, way back, to the beginning of everything, the Big Bang. That moment, or rather, that event, when space and time themselves seem to have started. We tend to think of the Big Bang like an explosion that happened inside space at a particular time, but that's not how physicists describe it. They say the Big Bang wasn't an event inside time, it was the origin of time and of space too. There was no before in any ordinary sense, no place it happened inside of, no ticking clock that led up to it. So what does that mean? If time started then, what about before? Can you even say before if there's no time? It's like asking what's north of the North Pole. The question sounds normal, but it breaks down when you really try to point somewhere. There is no further north. The concept stops applying. The same might be true of time. Maybe asking what came before the universe is like asking what's further up once you've reached the ceiling of a dome. There's no more up. Not in that direction. It's not that something is hidden from you. It's that the question itself needs a different frame. But we're not rushing to conclusions. We're just noticing how the ground starts to shift under these questions. Time feels so natural, so familiar, but the closer you look, the more mysterious it becomes. Let's stay with the idea of motion. The ticking of a second hand, the orbit of the moon, the pulse of a heart. We use change to feel the passage of time. But what if nothing changed? Not just in your room or in the world, but in all of space. If nothing moved, if every atom froze, would time still exist? This isn't just a thought experiment. It touches on something real in physics. In many of the deepest equations, especially in quantum mechanics and general relativity, time doesn't always appear. The formulas describe how states relate to each other, but not necessarily how one unfolds into another. It's the relationships that matter, not the clock on the wall, and yet you're experiencing something now. This sentence, this breath, this moment, it's passing, or seems to be. So whatever time is, it's tied to your experience, maybe deeply so. Some physicists have even suggested that time is not fundamental, that it might be an emergent property, something that only exists when certain conditions are met, when matter behaves in particular ways, when entropy increases, when observers like you or me are there to notice. If that's true, then in a universe with no matter, no observers, no change, time might not be real in the same way. It might not exist at all. But that's just one path. Others argue the opposite, that time is fundamental and space emerges from it. That in the deepest level of physics, time ticks on even if nothing else happens. There's no experiment yet that can tell us for sure. So back to the question. If there were no universe, no stars, no particles, no fields, no geometry, would time still be there? Could it be? Some thinkers say no. Without change, without relationships, without the physical laws unfolding, there's no meaning to the word time. Nothing to measure, nothing to compare, nothing to pass. Time is a label we apply to sequences of events. If there are no events, there's nothing for time to do, but others say yes. Time might be the background on which any universe could arise. Not a thing that starts, but a condition that always is. It's a hard idea to grasp because we've never experienced a universeless time. We only know what it's like to live within time, not outside it. And that brings us to something quiet and personal. You. You're a creature made of memory. Your sense of self is stitched together from the order of events you remember. You wake, you move, you speak, you feel. Each of those has a place in your inner timeline. That's how you know who you are, and it's how you know when you are. But what if memory is what creates the sense of time? What if the past isn't something out there, but something your brain records and organizes? If that's true, then time might only be real for beings who can remember, or forget. You're not being asked to choose a side, only to float among these ideas, slowly, thoughtfully, without needing to land. The journey is just beginning. We've only started to loosen the edges of what time might be. In the next part, we'll start asking how time behaves inside you, how your body and mind track it, sense it, rely on it, and what happens when they don't. Because before we can understand whether time exists without the universe, it helps to understand how deeply time lives within us. It's easy to think of time as something we understand. Everyone uses it. You ask what time it is. You wait for a time to pass. You make time for someone or run out of time entirely. But all of those are just expressions built on a feeling that something is always moving forward, steadily, invisibly, and without any way to stop or reverse it. The question is, what exactly is that movement? And is it something real in the world, or just something in your head? The most common way people describe time is as a kind of river, a flowing stream that carries us from moment to moment, always moving in one direction. But even that image hides a problem. If time is flowing, what is it flowing through? If it moves, what does the moving? If you try to define time as the thing that keeps everything from happening at once, it sounds simple until you start to look at it too closely. One way to begin is to ask what it means for something to happen. For a thing to happen, there needs to be change. A sound begins, a light turns on, a foot touches the ground. Change is the signal that something has taken place. And we use those signals to build a sense of before and after. Without them, all you have is a frozen picture. No story, no direction, no time. But here's where it becomes strange. Time isn't a thing you can see or touch. You don't open a box and find a scoop of time inside. You only see its effects, a candle melting, a child growing, a tree bending in the wind. These aren't time themselves. They're changes that you interpret through time. That means you can't really point at time. You can only point at something that has changed and say time has passed. So maybe time is just our way of keeping track of change. But what does that mean for places where nothing changes? Imagine a room sealed away from everything. No sound, no movement, no ticking. If you went in and came out later, you'd say time had passed. But if nothing inside the room changed, would time still have meaning there? Or does time only become real when something happens? Some physicists lean toward that second idea. In many of the deepest theories about the universe, time doesn't show up the way you might expect. In the equations of quantum mechanics, for instance, systems can be described in ways that don't use time at all. They describe states and the probabilities of those states, but not the exact steps between them. It's as if time is an afterthought, something that emerges once the rest of the picture is complete. There's another place where time gets slippery, general relativity. In that theory, time is part of space-time. It's not separate from space, but woven into it. When something heavy sits in space-time, it bends both space and time. That means time doesn't tick at the same rate everywhere. It runs slower near big masses, faster where there's less gravity. On a tall mountain, your watch actually runs slightly faster than it does at sea level. You don't feel the difference, but it's there. This shows us that time isn't universal. It's not one big clock ticking the same everywhere. It's local, personal, dependent on where you are and how fast you're moving. Einstein called it relative, and the experiments keep proving him right. So what does that mean for what time really is? If it's not absolute, if it can bend and stretch and even vanish from some equations, then maybe it's not a fundamental part of the universe after all. Maybe it's more like temperature, something that's very real and very useful, but which only exists in systems made up of many parts. You don't talk about the temperature of a single atom. It doesn't make sense. You need a collection of particles, a system. Then temperature becomes real. Maybe time is like that. Only meaningful in certain contexts. Only real when enough things are changing and interacting. That idea leads to the notion of time as emergent. It means time isn't part of the deepest layer of reality. It's something that appears when certain patterns come together. Like a wave on the ocean, it looks like a thing, but it's really just the result of many water molecules moving in a coordinated way. There's another piece of this puzzle too, entropy. In thermodynamics, entropy is a measure of disorder, or the number of ways a system can be arranged. It turns out that this idea gives us the arrow of time. If you start with a low entropy system, like a neatly stacked set of blocks, and let it evolve, it naturally moves toward higher entropy, a messier, more disordered state. The stack falls, The pieces spread. That's the direction we experience as forward, but the laws of physics don't actually care which direction time runs. If you watch a video of two billiard balls colliding, it's hard to know if the clip is playing forward or backward. The equations work either way. So why does time feel like it only moves in one direction for us? Because of entropy. Because the universe started in a very ordered state, and ever since then, it's been sliding toward more disorder. That's not something you feel consciously, but it underlies your whole experience. A cup falls off a table and breaks. You never see it unbreak and jump back up. The glass shatters, the milk spills, the heat spreads out. That's the arrow, the one-way road. But this raises another question. What if the universe had started in a high entropy state? Would time feel different? Would it exist at all? Or is time just our way of describing the path from order to disorder? When people say time is an illusion, they often mean that this one-way flow is something your mind creates, not something built into reality. The brain remembers the past. It doesn't remember the future. That gives you a feeling of direction. But maybe that's all it is, a feeling, a consequence of how memory works, not of how the universe does. Still, the feeling is persistent. You can't just decide to stop experiencing time. Your thoughts have a rhythm, your senses have a delay. Your awareness flickers moment by moment. There's no turning that off. So maybe asking what time really is like asking what now really is, or what here means. It's less about some grand external thing, and more about the structure of experience. Your brain has mechanisms that help you track time. You've got circadian rhythms, which cycle roughly every 24 hours. You've got internal clocks that let you tap a beat, estimate durations, wait your turn in conversation. But none of these are perfect. They drift. They get distorted by emotion, attention, context. Time flies when you're engaged. It drags when you're bored. It vanishes in sleep. Your perception of it is flexible, which makes sense if time isn't fixed to begin with. Even language changes how you think about time. Some cultures describe the past as being in front of them because they can see it. The future is behind because it's unknown. Others do the reverse. Some people think of time as a line they travel along. Others see themselves as stationary, with events flowing past. The point is, there's no single way to picture it. And that hints at something deep, that time isn't an object, it's a model, a map your brain builds so you can navigate change. So maybe time is the name we give to change we can't control, or the structure we overlay on experience to make it intelligible. Or maybe it is fundamental, just not in the way we usually think. There are theories where time exists, even when nothing else does. It ticks quietly in the background, like a metronome waiting for the first note. In these views, time isn't tied to motion or memory. It's just a dimension, one that keeps going, whether anything uses it or not. But that leads to a different kind of strangeness. If time is there without a universe, what exactly does that mean? What is it moving? What marks its passage? If absolutely nothing is changing, no fields fluctuating, no particles existing, then what distinguishes one moment from the next? Could there even be a next? At that point, the question starts to collapse into itself, like trying to imagine color without light. You know the word, you know what it refers to, but without the thing it describes, it becomes empty. And maybe that's the key to understanding what time is. Maybe time doesn't exist on its own. Maybe it's a property of systems like motion or shape or temperature. Something that emerges when things interact, when there's difference, when something can happen. You can't have a melody with only one note, and maybe you can't have time with only one state. Still, the question lingers. If time is only real when the universe is, does that mean it had a beginning? And if it had a beginning, can it have an end? Those are questions we'll step into slowly. Because before we can answer whether time existed before the universe, we need to ask whether it even makes sense to talk about a before when there's no time to begin with. So far, the question has moved outward, into physics, into space-time, into the fabric of the universe itself. But to really understand time, it also helps to go inward, not into theory or equations, but into your own body, into the way time lives in you, measures you, regulates you, often without your awareness. Right now, as you listen, your body is tracking time. It's doing it with hormones, neurons, electrical pulses, and subtle rhythms that have been developing since before you were born. You have clocks inside you, not just one, but many, and they don't tick like the ones on the wall. They oscillate, they drift, they reset. And somehow they keep you moving in rhythm with a whirl that doesn't stop. The most well-known of these internal clocks is your circadian rhythm. It runs on roughly a 24-hour cycle, and it's built into the biology of nearly every living thing on Earth. It's the reason you tend to feel sleepy at night and more alert during the day, even without looking at the sun. It's not a perfect clock, but it's regular enough that your body uses it to time all kinds of internal processes. When to release melatonin, when to raise your body temperature, when to feel hunger, when to dream. This rhythm isn't just a background process. It affects how fast wounds heal, how your memory works, how likely you are to catch a cold. Shift it too far out of sync, and things start to fall apart. People who regularly work night shifts or travel across time zones often feel the consequences: fatigue, confusion, immune problems, even long-term health risks. Because your body doesn't just exist in time, it depends on a sense of time to stay balanced, but the circadian rhythm is just one part. Inside your brain, in a region called the suprachiasmatic nucleus, a small cluster of cells just above where your optic nerves cross, you have what's often called your master clock. It receives signals about light from your eyes and uses that information to keep your rhythms aligned with the day-night cycle of Earth. This is your internal anchor to the outside world's time. If that signal is missing for too long, your clock begins to drift. Yet even without sunlight, your body keeps time in its own way. It doesn't rely on gears or springs. It relies on proteins that build up and break down in irregular cycles, on genes that switch on and off at predictable intervals, and on feedback loops that sustain those rhythms across billions of cells. Each part of you contributes to your sense of temporal order. Then there are the smaller clocks. You have systems that track shorter durations, seconds, minutes. These aren't tied to the sun. They're more connected to your attention, your movement, your focus. When you tap your foot to music, estimate how long a moment will last, or wait for a page to load, your brain is using internal timing systems that rely on pulses and oscillations in neural circuits. These mechanisms don't measure time in the abstract. They generate patterns that help you coordinate action. But these patterns aren't always accurate. In fact, your sense of short durations is remarkably flexible. Emotions change it. Context changes it. If you're scared, time feels like it slows down. If you're bored, it seems to drag. In danger, a few seconds can feel stretched into minutes. That's not just an illusion. It's how your brain recalibrates when it senses urgency. When something critical is happening, your perception of time adjusts to give you more resolution, more awareness per second. Not because time itself changes, but because your attention sharpens. That's one of the things that makes time so difficult to pin down. It behaves like a physical dimension in some contexts, but like a psychological state in others. It bends under gravity, yes, but it also bends under memory, mood, and attention. Memory might be the most important part of this. Without it, time doesn't just feel different, it becomes meaningless. You could sit in a room where nothing changes, no sounds, no lights, no interruptions. If your memory were wiped every few seconds, that room wouldn't feel timeless. It would feel like nothing at all. Time isn't just a matter of what's happening, it's a matter of what you can compare the present to. This is why some people experience time differently after trauma, or under the influence of certain drugs, or with certain neurological conditions. In those states, the brain's ability to track sequences, store events, and judge durations gets altered. Time can feel too fast, too slow, too jagged, or even suspended. It's not the universe that has changed, it's the internal machinery that interprets it. Sleep plays a key role here too, not just as a rest from time, but as a kind of reset for how you process it. When you dream, your perception of time can become completely untethered. A few seconds of real time can feel like hours in a dream. Events loop, sequences fracture, time becomes fluid. yet your body continues to follow its rhythm. Your breathing slows, your muscles go still, hormones cycle, your cells repair themselves on schedule. Even in sleep, the body's clocks are quietly ticking. This shows how layered your experience of time really is. On the surface, you have conscious awareness, the story of now, the sense of flow. Below that, memory, sequences held together into a timeline, and below that, rhythms, chemical, biological, neurological, all of them trying to stay in sync, not just with the universe, but with each other. When they fall out of sync, you feel it. Jet lag, sleeplessness, confusion, a mismatch between what the world is doing and what your body expects. It's not just uncomfortable, it's disorienting. Because deep down, your sense of self depends on continuity, a thread that runs through waking and sleeping, through thought and sensation, through what happened and what's happening now. This is where it gets interesting in the context of our larger question. If the universe didn't exist and there were no physical clock, would time exist in any meaningful way? Based on everything you've just considered, the answer might depend on how you define exist. Because time, for you, isn't just something out there. It's a structure your mind builds from memory, rhythm, and expectation. If all of those disappeared, time wouldn't just become hard to describe, it might stop having any use at all. But there's another way to look at it. Imagine a single person, floating in empty space with no objects around, no lights, no sounds, just consciousness, no sun, no moon, no stars. Would that person still feel time? The answer might be yes, but differently. They would still have a heartbeat, still experience hunger, still feel thoughts rise and fall. They might have no way to measure time precisely, but they'd know that things are unfolding, that one moment leads to another. Now imagine that person has no senses at all, no memory, no input, no awareness of thought, just raw existence, unmarked. Would time still mean anything? It starts to blur. Without change, without memory, without contrast, time becomes invisible. Not absent necessarily, but unreachable. The clock is there maybe, but there's no one to watch it tick. This takes us back to the idea that time might be relational, not a standalone substance, but a description of how things compare, how one event follows another. Without events, there's no ordering. Without ordering, there's no timeline. Without a timeline, there's no past or future, just a kind of unbroken sameness. And that leads to another thought. Maybe the question isn't whether time exists without the universe, but whether anything can exist without contrast, without difference. If all you have is one state, frozen, unchanged, with nothing outside it to compare against, can you even say it is anything? Even your own sense of self depends on contrast. You are who you are partly because you know who you were. You measure change. You notice the differences. That's how identity forms. It's how memory links. And all of that rides on the back of your inner clocks. The universe may have its own time measured in space-time curvature and thermodynamic entropy, but you have yours too, tied to light and sleep and memory and emotion. Your brain turns time into experience. It doesn't just count it, it gives it meaning. And that meaning is what keeps everything aligned. You wake, you notice, you remember, and you move forward even when standing still. But if your experience of time is built from inside, what happens when we step outside again? When we leave the body, leave perception, and ask about the state of things before any awareness existed, can we talk about a before, when there was no observer, no memory, no flow? We're getting close to something harder to hold. The moment just before everything began. Or maybe not a moment at all, maybe something else entirely. Earlier, we looked inward, at how your body tracks time, how memory holds sequences, and how rhythm anchors your experience. But what if we take that understanding and apply it to something even quieter? Not to a person, not to a mind, but to a space where nothing moves. No light, no change, no noise, no drift, just stillness. What happens to time when there is no motion? On the surface, the answer seems easy. you'd still say that time is passing. A frozen lake may look still, but time keeps ticking. Ice molecules still vibrate, even if slowly. Atoms still move. The Earth keeps spinning. The sun keeps rising. So even if nothing appears to be happening, something still is. But what if that isn't true? What if you imagined a place where everything had genuinely stopped? Not just a paused video or a statue frozen in time. Not just silence or slowness. Actual stillness. Every particle, every photon, every vibration, motionless. Would time still apply? This question isn't just philosophical. It points directly at how we define time. If time is what measures change, then in the complete absence of change, time might become undefined or meaningless. You could say time is still there, but it has no function, like a ruler in a world with no length, or a clock in a room with no movement. In physics, the idea of time is tied closely to what happens. In Newton's view, time was absolute. It moved at a steady rate everywhere, no matter what. It didn't care whether anything moved. It simply advanced. But in modern physics, that idea is replaced. Time is relative. It bends depending on speed, gravity, and motion. If nothing moves, if nothing interacts, then time may lose its meaning entirely. Think about a clock. Any kind of clock. Digital, mechanical, atomic. What is it really doing? It's marking intervals. Something oscillates. A gear turns. A wave vibrates. That regular motion is what we call timekeeping. It's not the numbers that make it a clock. It's the movement. Now remove that movement. There's nothing to count, nothing to measure. The clock doesn't break, but it becomes silent. Functionally, it stops. Some physicists go even further. In certain interpretations of quantum mechanics, the idea of time doesn't appear at all in the basic equations. Instead, what matters are correlations between states. You don't get one thing happening after another. You just get a network of relationships. What depends on what? The sense of order, of flow, of this before that is something we overlay. It's not built in. If that's true, then time may not even be a background we move through. It may be a tool we use to describe when and how systems change. Not a flowing river, but a label for connections, for cause and effect. That changes how we think about stillness, because a moment without movement might not be a moment at all. If nothing changes, there's no sequence, no story, no contrast, just a state, whole and unmoving. You can't say whether it lasted 1 second or 1,000 years, because those words have no reference point. This is where the idea of timelessness starts to take shape, not as something exotic, but as the natural consequence of total sameness. If a state doesn't evolve, doesn't shift, doesn't produce any detectable effect, then no clock in the universe, external or internal, could say how long it lasted, because the answer would be based on nothing. There's a similar idea in general relativity. In extreme environments like the edge of a black hole, time stretches. As you get closer to the event horizon, the point of no return, time from your perspective moves normally. But to a distant observer, your movement appears to slow down. If you could hover just above the horizon, you might witness the universe rush by, while you remain nearly motionless. And from the universe's view, your time would almost stop. Now take that concept and remove the mass, remove the curvature, remove even the observer. Imagine an empty place with no fields, no forces, no particles, no waves, no clocks to run, no signals to track. Could you say time exists there? You might want to say yes, that it's there, just waiting for something to happen. But then what makes that a meaningful statement? If nothing happens, and nothing ever can happen, is there any difference between saying time passes and saying nothing at all? It's like imagining a perfectly flat line. No hills, no valleys, no curves. Just flatness forever. It exists, but it has no features, and in that sense it resists description. There's nothing to measure, no beginning, no end, just a surface with no distinction. The same may be true for a universe, or a condition without movement. It's not that time ends, it's that it stops mattering, it loses definition. In the lab, scientists have tried to explore this by cooling matter to to near absolute zero. As the temperature drops, atomic motion slows. At absolute zero, theoretically, all motion would cease. In practice, we can't reach that limit, but we can get close. And as we approach it, time, at least as measured by atomic vibration, begins to stretch. Processes slow, events delay. The system begins to resist change. This gives us a kind of hint. That time isn't something separate from what's happening, it's what we call happening. Stillness, then, becomes more than just the absence of motion. It's the threshold where time becomes meaningless, not because it disappears, but because it becomes indistinguishable from nothing. And yet, there's another layer. Because you're listening to this now, and the words are passing one after another, and even if you imagined perfect stillness, you'd be doing it in order. One thought, then the next. That sequence is hard to let go of. Your mind insists on continuity. Even when nothing is happening, it needs something to follow. This may be why timelessness is so hard to grasp. You can think about it. You can try to picture it. But the very act of thinking is structured in time. Your neurons fire in sequence. Your memories arrange events. You can't escape the rhythm, even in imagination. So perhaps the reason we struggle to describe a moment without movement is because we're built entirely from movement. Electrical impulses, chemical exchanges, cellular cycles, breaths, heartbeats, all of it is motion. No part of you is truly still. And so the idea of stillness, a genuine, universal, absolute stillness, remains alien. That doesn't mean it's impossible, only that we have no experience of it. If such a state exists, it may lie beyond what consciousness can ever feel, or even ask about. But there's something else to consider. What if the universe began in stillness? What if, before all movement, all expansion, all light, there was a condition where nothing changed? Could that have been timeless? Or was it a kind of hidden time waiting to be released? In some theories of cosmology, the early universe wasn't born from an explosion, but from a transition. A sudden shift from a symmetric, changeless state into one where space and time, as we know them, could unfold. That initial condition might not have had any direction, any evolution, any events. But once that symmetry broke, once the first fluctuation occurred, everything changed. Time, in that view, didn't begin at zero. It began when change became possible. And if that's true, then maybe there was no first moment in the way we think. Maybe there was only a transition from timelessness to timefulness. Not a bang, just a shift, a whisper of difference, the smallest imbalance. It's not something we can observe directly. We can't rewind the universe to the moment before its beginning. But we can ask whether such a moment makes sense, whether there's any way to talk about before without time. And that leads us toward the edge of the next idea. Because if motion brings time into being and stillness erases it, then what existed before the universe, if anything did, may not be a question of time at all. It may be something else, something that doesn't follow our rules of before and after. So what do we call that? We've been thinking about time as something internal, something felt, something tied to movement. But if time comes from change, then where does the change come from? Not just in us, but in the universe itself. If time seems to flow, is that because the universe is doing something that causes it to? Is the universe itself ticking, like some vast cosmic clock? The idea sounds simple at first. A clock ticks, the universe changes. Maybe it has its own rhythm. But that comparison brings with it a lot of assumptions. A clock is a device designed to mark intervals. Its gears move in steps. It divides time into units, seconds, minutes, hours. But the universe wasn't built to tell time. It wasn't made with ticks. It doesn't count anything. So to ask whether it ticks is to ask whether there's some fundamental rhythm underneath reality. A beat, a pulse, something regular and universal that everything follows. Physicists have looked for something like that. They've tried to find the smallest possible unit of time, a kind of indivisible moment, below which nothing more basic can be said to happen. That's where the Planck time comes in. It's an incredibly small slice of duration, about 10 to the negative 44 seconds, not a human second, but a theoretical limit. The idea is that below that scale, our concepts of space and time break down. Quantum uncertainty becomes so extreme that time itself may lose its meaning. But even so, the Planck time isn't a tick, it's a boundary. It doesn't mean the universe operates in steps of that size. It just means our tools can't describe anything smaller. That still leaves us with the question, does the universe evolve in steps, like frames in a film, or is it continuous? Does time glide smoothly, or does it jump? Some interpretations of quantum mechanics suggest that time might not be fundamental at all, that what we see as change, one thing becoming another, is just a shift in the relationships between quantum states. No background clock, no ticking, just different arrangements that we interpret as motion. And yet the universe behaves in ways that suggest regularity. Light travels at a constant speed, particles oscillate with specific frequencies, atoms release energy in precise amounts. We use those patterns to define our units of time. 1 second officially is based on the vibrations of a cesium atom. That's about 9 billion cycles per second. So when we say the universe ticks, we're really saying we've found things in it that repeat reliably enough for us to use as reference points. But those reference points are human choices. They work because the laws of physics allow them to, not because the universe designed them to be used that way. There's no cosmic second hand sweeping across the sky, no countdown echoing through space. What we're left with is a picture that's both steady and strange. On one hand, the universe does evolve. It changes. Galaxies form, stars die, atoms decay. On the other hand, the idea of a global clock, a single ticking mechanism that governs everything, doesn't hold up under scrutiny. In general relativity, time isn't a single thread running through the cosmos. It's a web, a mesh of individual timelines, each shaped by motion and gravity. That means two people in different places might experience different amounts of time passing between the same two events. One near a black hole, one far away. Their clocks drift. Their seconds disagree. Time isn't wrong for either of them. It's just local. So if the universe doesn't have one clock, does it have any? Maybe not in the traditional sense, but it does have structure, and that structure unfolds in ways that can be measured. One example is cosmic expansion. Since the Big Bang, space itself has been stretching. That stretch isn't ticking in steps, but it does happen at a rate. We can measure how far apart galaxies move over time. That gives us a kind of large-scale rhythm, not a tick, but a trend, a background process we can observe. Another example is radioactive decay. Unstable atoms break down over time, and they do it with statistical regularity. You can't predict exactly when one atom will decay, but you can say how many out of a group will decay in a certain amount of time. That statistical behavior gives us another kind of clock, a probabilistic one. These clocks aren't synchronized, they're not linked to a master timer, but together, they give us a picture of a universe that evolves in regular, measurable ways. That's the closest thing to ticking we've found. But the deeper you go, the harder it becomes to say what's actually changing. In many formulations of physics, change is just the difference between one state and another. The equations don't include a now. They don't say which way time flows. They just show relationships from one configuration to the next. In some approaches, time is removed entirely. In the Wheeler-DeWitt equation, for example, a key part of quantum gravity, there's no time variable. The equation describes a universe where all possible configurations exist, but not in sequence. There's no ticking, no movement, just a static landscape of possibilities. So how do we reconcile that with what we feel, with the obvious fact that we experience time passing? One answer is that time, as we know it, might emerge from entanglement, from how subsystems relate to one another. Imagine you have a closed system, like the entire universe. From the outside, it may not change at all, but from inside, parts of it can appear to change relative to each other, and that's enough to give rise to what we call time. This is sometimes called the Page and Wouters mechanism. The idea is that time isn't fundamental to the universe as a whole, but it emerges for observers inside the universe because they can track correlations between things. You can't see the whole system, but you can see part of it and measure how it shifts compared to something else. That means the universe might not tick on its own, but to beings like us, embedded within it, it looks like it does, because we're part of those shifting correlations. We are change, measuring change. This view doesn't make your experience any less real. You still wake up, eat, sleep, grow older. You still remember yesterday and anticipate tomorrow. The difference is that those experiences aren't being driven by an external metronome. They're emerging from the structure of relationships between particles, between fields, between moments. So maybe it's not that the universe ticks, but that it allows ticking to happen. It contains systems that oscillate, that evolve, that decay. And from those we build our clocks, not just physical ones, but mental ones, social ones, cultural ones. It's also worth noting that our sense of time's passage, the steady, continuous flow, is something we bring to the equation. We impose rhythm. We notice cycles. Our brains evolved in a world of sunrise and sunset, heartbeat and breath. Our stories unfold in sequences. Our memories are laid out in order, so we interpret the universe through that lens. But outside of that interpretation, time might not flow at all. Nothing may be ticking. The universe may simply exist in a vast configuration space, with change being an illusion produced by partial information. If that's true, then our clocks aren't wrong. They're just contextual, local tools for local experience. They let us live in time, even if the universe itself lives beyond it. And yet, we still ask the question, still wonder whether something is ticking out there. Not because we expect to hear it, but because we want to understand what drives the rhythm we feel inside. The next step is to follow that rhythm backward, not just to the beginning of your own awareness or to the rise of stars and galaxies, but all the way to the edge of the known, to the start of expansion, to the moment when everything began to move, and to ask what time looked like at the very start of the universe. The idea of a first second sounds simple, like the start of a race. One moment, nothing. The next, everything begins. But in cosmology, that first second holds layers. It's not just the beginning of the universe, it's the beginning of meaning, the start of space, time, energy, matter, and the physical laws that would shape everything that followed. And somehow it all happened in less time than a breath. We call it the Big Bang, though the name is misleading. It wasn't a bang in the way we think of explosions. It wasn't something that happened in space with debris flying outward. It was the expansion of space itself. There was no center, no edge, and no outside to contain it. It wasn't the explosion of something into somewhere. It was the sudden appearance of space-time itself, everywhere at once. So what does a second mean in that context? Time, as we understand it, comes from sequence, from one state turning into another. But in that first second, everything was different. Not just the contents of the universe, but the structure itself. Space was expanding rapidly. Particles were forming. Temperatures were unimaginably high, and the laws of physics, or at least their earliest versions, were still unfolding. If we rewind to the beginning, we find a boundary we can't cross directly. The Planck time, that moment, about 10^43 seconds after the start, is the earliest we can meaningfully talk about. Before that, our current theories no longer apply. Quantum mechanics and general relativity stop agreeing. The math breaks down. We don't know what time looked like there, or even if "looked like" is a valid phrase. But just after that, within the first microsecond, things started to take shape. At first, the universe was incredibly hot and dense, too hot for particles to form in any stable way. It was a kind of soup, pure energy, tightly packed, uniform, chaotic. But as it expanded, it cooled, and that cooling allowed forces to split. First gravity, then the strong nuclear force, then the electro-weak force. These separations set the stage for everything else. Not just matter, but the behaviors matter could have. By about 1/10,000th of a second, quarks and gluons, the building blocks of protons and neutrons, started to stabilize. By 1 second, atomic nuclei could begin to form. Not full atoms yet, but the cores of them. The universe was still too hot for electrons to settle into orbit. That would take hundreds of thousands of years, but the foundation was being laid. From a physical perspective, the first second was a time of transitions, symmetry breaking, cooling, structuring. Space was inflating at an incredible rate. Distances between points grew faster than the speed of light, not because anything was moving through space, but because space itself was stretching. That's allowed under general relativity, and it explains why the universe appears uniform in all directions, why light coming from opposite ends of the sky matches so closely. Because in those first moments, everything was connected. But all of this, the cooling, the stretching, the formation of particles, it didn't happen on a schedule. There was no cosmic stopwatch counting out seconds. The idea of 1 second after the Big Bang is something we assign retroactively, based on models, based on how the universe behaves now. We look at particle interactions, background radiation, expansion rates, and we work backwards. We project what conditions must have been like and when. That means even the phrase "the first second" isn't absolute. It's meaningful to us, because we live in a universe with stable clocks, with systems that allow us to say what a second is. But in the first moments, those systems didn't exist yet. The ticking hadn't begun. What we call a second is based on the behavior of atoms under normal conditions. But nothing was normal then. Still, the physics gives us a picture, a timeline, a rough outline of what happened and when. Before 10 quantum 43 seconds, the unknown, quantum gravity territory. We don't know what ruled here. At 10 36 seconds, inflation begins. Space expands exponentially. By 10 32 seconds, inflation ends, and the universe fills with energy and particles. By 10 6 seconds, quarks bind into hadrons. By 1 second, neutrinos decouple, and nuclear reactions begin to shape the basic elements. Each step happened without pause. No separation between events, just a smooth transition from one state to the next. A cascade guided by cooling and interaction. Not driven by a master clock, but by conditions evolving naturally. And throughout all this, time, as we know it, was forming too. It wasn't something layered on top. It was part of the process. As space expanded, as particles appeared, as energy became structure, the framework for time emerged. Not necessarily as a thing, but as a description, as a way to compare one state to another. In that sense, the first second wasn't just a beginning, it was a transformation. From a condition where nothing could exist in a stable way, to a condition where lasting patterns became possible. But there's a larger question that follows. What set it in motion? Why did the universe begin at all? Why then, and not some other sub-moment? That's where the concept of time runs into its limits, because to ask why then assumes a before. It treats time as something already running, waiting for the universe to arrive. But most models of the Big Bang suggest that time itself began with the universe. There was no before, not in any meaningful sense. It's not that something happened before time, it's that before stops being a valid question. Like asking what's south of the South Pole. The concept doesn't apply beyond that point. So instead of asking what happened before the first second, we ask what conditions gave rise to it. Was it a quantum fluctuation? A random event? A transition from something else we can't yet describe? Some models suggest the universe could have emerged from a quantum vacuum, a state of lowest possible energy. Others suggest a multiverse, where universes bubble into existence, each with their own time and space. But in all these cases, time might be local, not global, not universal. That brings us back to the original question. What does it mean to have a first second, if time itself is part of the thing that started? Can we call it a moment if there was no ticking until after it began? It's difficult to imagine. We're used to thinking in sequences, in flows. But the first second of everything might not be a part of time. It might be time coming into being. And yet, here we are, in a universe with clocks, with order, with direction, which means whatever happened in that first second was enough to establish everything we see today. Galaxies, atoms, languages, thoughts. That first second left behind a signature. The cosmic microwave background, a faint glow that fills space, gives us a snapshot of the universe as it was just a few 100,000 years after that moment. It shows us the early patterns, the seeds of structure, and from that, we know something remarkable happened. Something precise, something incredibly powerful, yet somehow balanced enough to allow complexity to grow. We can't see before it, not yet, maybe not ever, but we can see what came out of it. And that tells us the first second wasn't empty. It was everything. The question now is what that everything came from, and whether time, real, flowing time, was already there to witness it. The phrase before the beginning is easy to say. It fits into sentences. It shows up in myths and origin stories. It sounds like something you could imagine. But the closer you look, the harder it is to hold on to. Because if the beginning is the start of time, then before doesn't point to anything. It becomes a word without a reference, and still, we try to use it. Still, we ask what was there before anything was. Part of the reason is habit. We live in time. We measure our whole lives by sequences, causes and effects, befores and afters. So when we hear the beginning of the universe, it's natural to ask what came right before, what caused it, what pushed it into motion. But that instinct might be wrong, not because the question is foolish, but because it assumes the rules stay the same even when everything else disappears. According to the standard cosmological model, the universe, including space and time, began around 13.8 billion years ago. That beginning isn't a point in space. It's a moment when space-time itself started to expand. There wasn't a location it came from. There wasn't an empty void it entered. There was just the start of existence as we know it. The question, what came before, assumes that time was already in place, that there was some sort of stage or container that held the beginning. But that's not what the physics suggests. The physics says time and space emerged together. They weren't sitting there, waiting. They weren't empty boxes. They were part of the event. So when we say, before the beginning, we're asking about something outside the structure of time. Not earlier, not in sequence, something else entirely. In general relativity, space-time is a geometric object. It curves and bends under the influence of mass and energy. But at very small scales near the start of the universe, quantum effects become important. That's where quantum gravity would take over, if we had a complete theory. But right now, that's still an open area, so we're left with possibilities, not conclusions. One possibility comes from quantum cosmology. In some models, the universe didn't begin from nothing, but from a quantum state. A timeless high-energy condition where space and time didn't yet exist in the way we understand them. This state wasn't empty. It had structure, governed by laws we're still trying to understand. Then, under the right conditions, a fluctuation occurred, a transition from timelessness into space-time. This isn't a before in the usual sense. There was no ticking clock in that state, no flow, just a configuration that allowed for time to emerge. In these models, the universe didn't explode into being, it tunneled into it. The process is more like a phase change than a creation. Another possibility is that the universe is part of a larger multiverse. In that view, our universe is one bubble among many. Some theories suggest these bubbles form in a broader inflating space, where universes constantly bud off, each with their own space-time. Ours had a beginning. But the inflating field it came from may not have. That field could be eternal, stretching forward and backward beyond our reach. If that's true, then before the beginning might point to something real, but not part of our timeline, a parent process, a deeper layer of structure. But even then, time may not be continuous across those layers. What looks like before, from our point of view, might be completely disconnected from what came next. Like two rooms with no door between them, You can imagine one next to the other, but there's no way to cross from one into the other. In other models, time might be cyclic. The universe expands, then contracts, then expands again. In that case, the beginning of our universe could be the result of a previous collapse. Time wouldn't have started at the Big Bang. It would have reset. That would allow for a kind of before, not an infinite past, but a looping one. One where beginnings follow endings in a closed sequence. But even there, time may behave differently near the turning points. The transition between collapse and expansion might blur the flow of time. It might bend it, fold it, or eliminate it altogether for a brief moment. The math becomes difficult. The meaning becomes unclear. Another idea comes from loop quantum cosmology, where space and time are quantized, made of tiny, discrete units. In some versions of this theory, the Big Bang is replaced by a big bounce. The universe contracts to a small but finite size, then rebounds into expansion. Again, time might continue across that bounce, but it would be a different kind of time, governed by quantum rules, not classical ones. These theories are attempts to extend physics to its limits. They're speculative, but they're based on known principles. They try to answer what came before, not with poetry, but with structure, not with stories, but with models. But all of them face the same problem. Our concepts break down at the beginning. Our words lose their footing. Before might simply not apply, not because nothing existed, but because the kind of existence we're trying to describe doesn't involve time at all. Imagine a state with no change, no motion, no memory, no cause and effect. Not a void, but a condition where comparison is impossible, where there's no past to contrast with the present, because present doesn't exist. That's what timelessness might mean. And yet, something changed. Something shifted. From that timeless state a universe emerged. Space began to stretch, matter formed, forces separated, and time, as we experience it, took shape. From that moment on, events could be ordered. Clocks could be built. Histories could unfold. The before may not be a place. It may be a boundary, a limit beyond which our understanding can't yet reach. Not because we lack imagination, but because the structure itself may not allow it. Still, the question persists, not because we can answer it cleanly, but because asking it helps us find the edges of what we know. Before the beginning might never give us a map, but it might keep pulling us forward, and maybe that's enough. Because as we move closer to that edge, another question appears. If the beginning is the place where time starts, what kind of place is it? What does it mean to have a beginning with no direction, no frame, no timeline? The idea of a place without before sounds impossible at first. It feels like a contradiction, like a story with no first page, or a road with no starting point. But when we reach the limits of time, it's exactly that kind of place we have to consider. Not because it makes sense in everyday terms, but because the structure of the universe itself may require it. Before is a word that only works when time is available. It depends on direction, on order. It assumes you can stack moments like cards, this one above that one happening after the other. But if time began with the universe, then stacking anything before it doesn't work. There's nothing to place the card on, no surface, no timeline. The stack doesn't exist yet. In our minds, place and time are deeply linked. Wherever you are, you're also when you are. But when we ask about a place without before, we're trying to picture location without sequence. A situation where position might exist but order does not. That's a hard thing to grasp because nothing in daily life prepares us for it. You walk through a room, you watch clouds move, you remember what happened an hour ago. These all depend on change over time. Take that away, and even basic concepts, cause, motion, memory, start to fall apart. Still, physics invites us to go there. Some theories suggest the universe began in a state with no time at all. Not a gap in time, not a pause, but a framework where time didn't apply. That's not the same as saying nothing existed. Something may have. But if that something didn't change or couldn't be measured against anything else, then it wouldn't have a before or an after. This isn't just a thought experiment. It shows up in the equations. In quantum gravity, some models describe the early universe using something called wave function of the universe. In those models, time doesn't appear. It's not part of the equation. The system is static. What we interpret as time comes later when we look at how different parts of the system relate to each other. In other words, time might emerge from correlation, not from some deep universal clock. In those scenarios, the universe didn't start with a tick. It started with a state, a kind of configuration that, under the right conditions, allowed time to appear within it. That starting point might have had geometry, energy, symmetry. It might have followed rules. But without anything to break that symmetry, without an event, a fluctuation, a crack, there would be no reason to say one moment followed another. The state just was. Without contrast, there was no time, not even stasis, because stasis is only meaningful in contrast to change. What happens when that symmetry breaks, when the state shifts, is what we call the beginning. But that moment wasn't preceded by anything, because there was no frame to support a sequence. It's not that something happened at a certain time, it's that time itself started happening. In that sense, a place without before is not empty. It's full of potential, full of possibility. But none of that potential is moving. It's all contained in a single timeless state, waiting for conditions that would allow unfolding. There's a term for this in physics, a timeless configuration space. Think of it as a map of all possible universes, all possible arrangements, not evolving, not layered in time, just existing. And from within that map, a specific universe might emerge, not because something made it happen, but because the structure allowed it, like a solution appearing from a complex equation, not caused, not triggered, just permitted. Once that universe exists, with expanding space, interacting matter, rising entropy, then time begins to make sense again. Things can change, events can be ordered, clocks can be built. But the frame they sit on didn't exist until the moment they did. This leads to an important shift in thinking. A place without before isn't nothing. It's not absence. It's a condition that contains the seed of time, without being in time itself. There are analogies to help make this clearer, though none are perfect. Imagine a frozen image on a screen. No movement, no sound, just a snapshot. You can describe the contents of the image, but nothing is happening. Now imagine that the image comes to life. Pixels start to shift, colors move, the picture becomes a video. The transition from frozen to moving is the closest we can come to imagining a transition from timeless to temporal. But in reality, there is no screen, no frame rate, just the system becoming dynamic. Another way to think about it is through dimensions. We often imagine time as a fourth dimension like height or width. But in some approaches, time might be more like a side effect, something that arises when certain conditions are met. Not a built-in axis, but a result of how space and energy interact. So in a place without before, dimensions may exist, fields may exist, but sequence doesn't. There's no ticking, no unfolding, no memory, just a state that has the possibility of containing time once the right changes occur. That might sound abstract. But it's a direction modern physics continues to explore, because it helps bridge the gap between general relativity, which depends on time, and quantum mechanics, which doesn't always need it. If we ever discover a theory of everything, one that fully unifies gravity and quantum mechanics, it may have to include this kind of timeless beginning, not because we want it to, but because time may not go all the way down. And that changes how we think about origins. If time is not fundamental, then neither is causality in the usual sense. There may be no first cause, no spark that lit the fire, just a condition that, under the right structure, allowed time and space to come into being together. This doesn't answer every question. It doesn't say what the condition was or why it existed. But it shows that asking what came before the Big Bang may not be the right kind of question. The answer may not be something we can place in time. It may only make sense as a kind of background, a structure without direction, waiting for time to emerge from within it. And that leaves us with something quieter, not a story of explosions and triggers, but a picture of a state that simply was, until it wasn't. The next step is to ask how that transition happens. What breaks the symmetry? What begins the unfolding? Once you begin to accept that time might not be fundamental, that it could emerge from something deeper, it's natural to ask what that something is. If time isn't just a container, not just an invisible line everything moves along, then maybe it has ingredients. Maybe it's made of parts, and if it is, then maybe it can be studied, changed, even broken. In daily life, time doesn't feel like a thing. You can't collect a pile of it. You can't point to a cup and say it's full of time, but that doesn't mean it isn't real. We talk about time passing, time being measured, time being wasted. We treat it as if it flows, but in physics, that flow isn't built into the equations. The laws don't say anything has to move forward. They just allow it. And that opens the door to the idea that what we call time might come from deeper processes, that what we experience as motion, duration, and direction could be the surface-level result of some internal structure. A structure that doesn't include clocks, but still creates what clocks measure. To see how that might work, think about temperature. Temperature feels basic. You know what hot and cold mean. But temperature isn't a fundamental thing. It's the result of many particles moving. Fast motion means higher temperature. Slower motion means lower. One particle doesn't have a temperature by itself. You need a collection. And when those particles behave in a certain way, the system gains a property. It becomes warm or cool, not because temperature is added in, but because it emerges from the system's behavior. Time might be the same. It may not exist at the smaller scales, but once you have enough complexity, enough matter interacting in the right ways, time appears, not as a substance, but as a property, something that makes sense only when patterns reach a certain level. This is what physicists mean when they say time could be emergent. They don't mean it's imaginary or false. They mean it's not built into the fabric. It's something that shows up when the fabric moves in the right way. So what would the fabric be? One idea is that space itself is made of discrete units, not smooth, not continuous, but quantized, made of tiny loops or nodes or patches depending on the model. In loop quantum gravity, for example, space-time isn't a background. It's a network, a vast web of connections constantly shifting. These shifts don't happen in time. They create what we interpret as time. In that view, time is the ordering of changes in the network. Each change isn't located in time. It is the time. You don't need an external clock. The system carries its own unfolding. That unfolding is slow, local, and relational. No master rhythm, no single arrow. Just a series of transitions that, from the inside, feel like the passage of time. It's not unlike watching a flip book. From outside, you can flip the pages fast or slow. You control the rate. But from inside the flip book, each image comes after the last. There's a direction. There's a flow, not because something's ticking, but because there's a structure to the sequence. Another angle comes from something called the thermal time hypothesis. This idea suggests that time doesn't come from the universe as a whole, but from the state of systems within it. It proposes that time is tied to entropy, the tendency of systems to become more disordered. The more ways a system can be arranged, the more entropy it has. And as entropy increases, time appears to move forward. This explains why you never see coffee jump back into a cup, or broken glass pull itself back together. The universe prefers to move from low entropy to high, and that direction is what we call the arrow of time. But the laws of physics themselves don't care which way the arrow points. The equations are reversible. They work the same in either direction. The reason you don't experience time running backward is not because it can't, but because the universe started in a low entropy state. That initial condition set the direction. From then on, higher entropy became more likely, and with that likelihood came what we call forward motion. So in this view, time isn't made of something physical. It's made of probability, of increasing uncertainty. As particles spread out, as systems mix, As options multiply, time emerges as the measure of that unfolding. There's another idea, even more abstract. In quantum mechanics, particles exist in a state of superposition, many possibilities at once. They don't commit to a specific state until they interact with something. That interaction is called measurement. But some physicists suggest that time, too, might be tied to that process, that each act of interaction, each update to the system, generates a new state, and those states line up into a sequence, not because time is passing, but because the universe is updating itself. From that perspective, time is the record of those updates. Each change becomes part of a chain. You don't need a clock. You don't need a metronome. Just one change after another. And from those changes, time appears. That would mean time is not a background, not a substance, not even a flow. It's an interpretation, a pattern that emerges when the universe shifts from one configuration to the next. The ingredients aren't seconds or minutes, they're transitions, quantum events, thermodynamic shifts, geometric reconfigurations. But here's where it gets strange again. If time is made of changes, then what happens when nothing changes? Does time stop existing, or does it keep going quietly in the background? In some cases, nothing changing might just mean you're in a static state, a moment that holds for a while, but if that moment has no internal difference, no contrast, then there's no way to measure how long it lasted. Time, without change, becomes invisible. And that matches what we saw earlier. Time may not be something you add to a system. It may be something that requires contrast to appear. No difference, no time. No sequence, no flow. So if time is made of something, it may not be a thing you can hold. It may be made of comparison, of structure, of possibility narrowing into outcome. And the ticking you feel might just be the sound of change happening. This leads to deeper questions. If time is built from change, and change depends on rules, then maybe time is rooted in the logic of the universe itself, not as a material, but as a framework, something like language, something that only becomes real when the symbols start to connect. And if that's the case, then time didn't begin in the universe. It began with the universe. As soon as the first distinction appeared, as soon as symmetry broke and states diverged, time came into focus, not as a thing, as a result. But if time is a result, not a resource, then that changes how we ask about origins. We don't look for a moment when time was born. We look for the shift that made change possible, the structure that allowed outcomes, the frame where transitions could happen. The question, then, is what kind of structure can support that? What kind of reality allows time to emerge at all? And can that reality exist without anything else? If time isn't a standalone thing, but something that emerges from change, then measuring it depends on more than just a ticking clock. It depends on comparison, on distance, on movement between points. And that brings up a natural follow-up. Can time be measured without space? At first glance, the two seem separate. We talk about space as where things are, and time as when they happen. But the more closely you look, the harder it is to pull them apart. Every clock depends on motion. Every measure of time depends on something moving from one place to another. Even inside your body, your sense of duration is tied to rhythms, patterns, cycles, all of which unfold in space. You could ask how long something lasted, but to answer, you'd need a reference, a vibration, a decay, a distance crossed. Something had to change in a way that can be counted. That change always involves space. Whether it's the swing of a pendulum or the oscillation of an atom, you're looking at movement through a dimension. That's not just a convenience, it's built into how physics works. In Einstein's theory of relativity, space and time are part of a single structure, space-time. You can't affect one without affecting the other. Moving through space changes how you experience time. The faster you go, the more time slows down relative to someone standing still. Strong gravity does the same thing. It curves space-time in a way that affects both where and when. That means time doesn't operate on its own. It bends with space. It stretches with gravity. It responds to movement. Without space, there's nothing for it to curve around, nothing for it to interact with. So in that framework, time is never truly isolated. It's always part of the geometry. That raises a problem when we ask whether you could measure time without space, because measurement requires separation. You need two states to compare, a beginning and an end, a marker and a change. If there's no space, where do you place the markers? You could imagine a single point vibrating or changing in some internal way, but even then you'd be forced to describe that vibration as occurring through something, even if it's just conceptual space. Otherwise, you'd have no idea whether it repeated, whether it had frequency, whether it continued. Even quantum systems, which are often treated as point-like, exist within fields. They have extension. They're part of a structure. Without that structure, there's no way to frame change. And without change, time stops being measurable. It's like trying to record the passage of time with no clock, no reference, no motion, and no memory. Even if you insist time is passing, you'd have no way to detect it. It would be invisible, not because it isn't real, but because it has no contrast to reveal it. In some interpretations of quantum gravity, space is made of networks, abstract graphs of relationships between elements. Time in those models doesn't exist globally. It comes from how parts of the network evolve relative to each other. And crucially, those relationships have a kind of spatial structure. Not in the classical sense, but in terms of connectivity. Points are linked. Connections shift. That shifting is what defines both spatial and temporal structure. So if you remove space entirely, no connections, no layout, no distinction between locations, then time loses its reference frame, not just practically, but conceptually. You have no stage for events to occur on, no distinction between here and there, and without that, now becomes undefined. This isn't just theoretical. In the math of general relativity, if you flatten out space, remove curvature, remove volume, remove all distances, time doesn't vanish, but it loses meaning. The equations still describe a parameter that could be labeled as time, but without spatial relationships to plug into them, nothing changes. The system becomes static. You can still run the clock forward in the equations, but the state stays the same. It's like pressing play on a paused video. Nothing moves, nothing evolves. In that case, time is still in the math. But it's a parameter, not a measurement. It doesn't connect to observation. It doesn't produce experience. So maybe the better question isn't whether time exists without space. Maybe it's whether time can be known without space, whether it can play any role. And most models suggest it can't, at least not in a way that gives rise to anything we'd call real. That leads to a deeper point. Our concept of time isn't just about sequences, it's about intervals, and intervals are spatial as well as temporal. You need something to bridge, to cross. Whether that's a beam of light, a moving object, or a decaying particle, it needs a framework to move through. Take light, for example. It travels at a finite speed, about 29792 kilometers per second. That number means nothing without space. You need a distance for it to cover. Time is defined by how long that takes. If you had no spatial interval, there would be no time to measure. Even at the quantum level, events are spread out. Particles have uncertainty in position, fields have extension, probabilities are distributed across regions. You can't collapse all of that to a true geometric point and still talk meaningfully about evolution. Without space, you might have a condition, a state, but not a process. And without process, there's no measure of duration. There's just the state itself, still, undivided. Some physicists suggest that in the early universe, near the Planck scale, time and space may have been indistinguishable, that they arose together from a deeper set of rules. Rules that describe changes in relationships, not in space or time separately. Only when the universe expanded and cooled did those dimensions separate into the categories we now use. If that's true, then trying to imagine time without space is like trying to imagine sound without vibration. You can define it maybe, but you can't hear it. It has no path to reach you. That also means our current view, with space on one side and time on the other, might be temporary. A phase, a way of organizing experience that works at the human scale but may dissolve when you zoom out far enough. In that deeper view, what we call time and space might both be projections, shadows of a more abstract structure, one that doesn't unfold in the way we imagine, one where distance and duration are not separate ideas, but aspects of the same fabric. So when we ask if time can be measured without space, the answer may not be no in principle, but no in practice, no in any way that matters to experience, to observation, to change. Without space, time loses its markers, its pulse, its scale. And with no markers, time has no contrast. And with no contrast, it becomes invisible. So we keep the two linked, not by choice, but by necessity. And we keep looking for the structure that makes them both possible, which leads to another layer of the question. If time and space emerge together, then maybe neither is primary. Maybe they both come from something deeper still. If space and time both emerge from something deeper, then trying to imagine what comes before them or beneath them means stripping away everything familiar. No distances, no motion, no sequence, not even stillness, because stillness is defined by contrast, by something that could move but doesn't. What you're left with is a condition that doesn't unfold, doesn't contain, and doesn't develop. A timeless void. Even calling it a void makes an assumption. A void is usually an empty space. But this isn't space. It isn't empty in the usual sense because empty requires something it could have contained. It's not black, because black is a color, and color is light, and light travels through space over time. It's not silent, because silence happens when sound could exist but doesn't. None of these ideas apply here. What you're trying to picture is something that can't be pictured. Not because it's mysterious, but because the tools we use to represent things, images, words, timelines, diagrams, all depend on time. Even your imagination is structured by it. When you try to visualize nothing, you usually imagine an empty, dark space. But that space has depth. It has direction. You're still working with elements of a universe. Take those away, and you have no location, no sequence, no edges. In physics, this kind of situation sometimes shows up in equations where variables cancel out, where nothing is defined because the terms that give shape to reality haven't been assigned values yet. It's not a failure of the math. It's a sign that there's no frame to describe the system, not just a blank slate, a lack of slates entirely. Some theories call this a pregeometric state. It doesn't contain space, but it might contain relationships. Not measured in meters or seconds, but in connections, raw, structureless potential for interaction. It's not clear whether this condition would have any kind of duration. That question assumes time exists, but in a timeless void, the answer may not be zero. It may be undefined. Quantum gravity approaches try to handle this by treating space-time as emergent. They model the universe as networks of interactions, and these interactions generate geometry. So if you remove the interactions, you remove the geometry. You get something before geometry, before location, before sequence. But again, before stops meaning anything in that setting. You're not looking at one frame and then the next. You're looking at a totality where frames haven't even formed. This doesn't mean the void is a cause. It's not the thing that triggered the universe. It's not a source in the traditional sense. It may not even be a state. It may be more like a limit, the outer edge of meaningful description. And yet, from this non-structure, a structure appears, not necessarily by decision, not through some physical push, just through the mathematical possibility that a configuration could arise, a ripple in a field, a break in symmetry, a fluctuation in what we might call the vacuum, even if that vacuum doesn't yet support space-time. In quantum field theory, fluctuations are normal. Even the lowest energy state, the vacuum, isn't completely still. It buzzes with temporary excitations, particles appearing and vanishing. But those fluctuations happen in space and time. They require a field, and a field requires structure. In a timeless void, you don't have that. You don't have anything to fluctuate in. But if you extend the idea, it's possible that even the potential for fluctuation could exist in a deeper way, as a purely mathematical object, like a solution waiting to be selected. Some physicists have explored this idea by asking whether the universe could arise from nothing, not from an empty vacuum, but from no space-time at all. A zero-energy system, one that sums to nothing but contains structured possibility. The idea is controversial and not universally accepted. But it's one attempt to define what a timeless void could mean, without leaning on images or metaphors. In those models, time doesn't begin until the system becomes asymmetric, until some state becomes more likely than another. That's when order appears, and from that order, a direction, a sequence, not imposed from outside but selected from within. In this view, the timeless void isn't an object, it's a context, a frame where frames don't yet exist. And once even the smallest contrast appears, something that can be compared to something else, then time begins to make sense, not as a ticking clock, but as a sequence of distinguishable states. The moment you can say, this is different from that, you can begin to define a before and after. But not until then. This makes time something that emerges with differentiation. Without that, you don't just lose clocks, you lose any reason to talk about when. There's no experiment you can do inside a timeless void, no observation you can make, no signal you can send. There's no inside at all. It's a boundary condition, not a place. A situation where possibility is suspended, not because it's prevented, but because it hasn't organized itself yet, and yet something changes, or appears to. That shift, the first distinction, might not be a loud event. It might be a mathematical fact, a transition from zero to something so small and specific that it doesn't make noise, doesn't emit light, but changes the rules enough to allow the next step. Maybe it's not even an event. Maybe it's a selection, a particular configuration becoming more probable, not through cause and effect, but through constraint. Out of all the ways nothing could remain nothing, one arrangement becomes possible, not necessary, just allowed. And with that allowance, a path opens. Time, then, may not be something added to the void. It may be the first kind of structure that removes the void. It's the start of difference, and difference is what builds motion, memory, and experience. So the question is no longer whether the void exists. It's whether that moment of emergence, the one where a system shifts from timeless to temporal, can ever be understood or even described. We can't step into that void, but we can keep asking what happens just after, not the moment of time beginning, but the first traces of how it behaves. The moment something shifts from being the same to being different, time begins to show itself. Not suddenly, not with a loud arrival, but as a quiet trace, a before and an after. It's not that time turns on, it's that change becomes possible, and from change, order, and from order, a kind of flow. But even as it begins to unfold, it remains something you can't hold. You can watch it, you can measure it, but you can't touch it. It's easy to think of time as something flowing past us, like water in a river. But the more carefully you look, the more that image falls apart. In physics, nothing actually moves through time. Objects move through space, and we describe that movement at different values of a time parameter. The equations work by mapping how a system evolves, but time itself doesn't drift past us like a substance. It's just the label we attach to the stages of change. Still, we feel it, not just in our bodies, but in our experience. That feeling of time flowing, of a present slipping into the past, is so consistent and vivid that we treat it as fundamental, but it may not be. The flow we experience could be entirely internal, a product of memory, awareness, attention. Our brains don't just process the current state of the world, they link it to previous states. They track differences, detect movement, predict outcomes. That constant updating gives rise to the sensation of time passing. But it may be more like a mental overlay than a physical fact, Experiments in neuroscience show that your perception of time can stretch or shrink depending on context. When you're anxious, time slows. When you're absorbed in something, it speeds up. The same amount of external change happens, but your internal experience of it warps. That doesn't mean time itself is changing, it means the mechanism that tracks it isn't fixed. That mechanism is rooted in memory. Without memory, there's no past, and without the ability to anticipate, there's no future. The present becomes unmoored, a collection of sensations without direction. That suggests the arrow of time, as you feel it, may not be a property of the universe. It may be a feature of the way your mind interacts with the universe, and yet, the flow still matters. Because even if time isn't a substance moving past us, change still happens. States evolve. Systems drift from one configuration to another. Those changes are real. They can be recorded. They can be predicted. The flow may be internal, but the structure underneath it is not. So what is that structure? In most physical theories, time is represented by a parameter. It's not a thing. It's an axis, a way to track differences. But that axis isn't always required. In certain formulations of quantum mechanics, the state of a system can be described without reference to time at all. What matters is the relationship between variables, the correlations. You can know that when one value is high, another is low. That doesn't require a timeline, just a pattern. In those systems, time appears only when you introduce an observer, someone measuring, someone comparing. Time becomes a way to organize the changes they detect. Not because the system has a built-in clock, but because the observer imposes one. That doesn't make time unreal. It makes it relational. The same happens in thermodynamics. The equations that describe entropy don't say time flows. They just say that systems tend to move toward more probable configurations. We interpret that direction as forward, but the system doesn't. It's not heading toward a goal. It's just evolving statistically. But once you live inside that system, with limited access to information, the increase in entropy becomes your arrow. It creates a direction, not a flow in space, but a line through changes you can't reverse. And from that line, you get a feeling. Not just that time moves, but that it moves in one direction. Still, that direction isn't built into the universe. It comes from initial conditions, from the low entropy state the universe started in. Had it begun with maximum disorder, time would still exist in the equations, but there'd be no structure to organize it. No flow to detect, just endless sameness, forever. So the flow we feel, the sense that we're moving through time, is a result of the universe not being like that. It's a result of structure, of boundaries, of unfolding complexity. But it's not a substance. It's not something we can step outside of or grab hold of. You can't slow it down by touching it. You can't speed it up by pressing forward. You can only move through configurations moment by moment and record the differences. Even clocks don't experience time. They just change in ways we've agreed to use as references. An oscillating crystal, a decaying particle, a swinging pendulum, they all undergo repeatable transitions, and we count those transitions. That's it. That's the measurement. But the measurement isn't the thing. The flow we feel is not the ticks we count. It's something else. Maybe not a thing at all. Maybe just a shape in the way we organize experience. And yet, we all agree it's happening. The future becomes the present. The present becomes the past. That change happens in one direction, and not the other. The universe seems to care about that direction, not in the laws, but in the way things play out. That tension between timeless laws and a time-filled experience remains one of the central puzzles in physics. And there's no clear resolution yet. Some argue that time is fundamental, others say it's emergent. But both sides agree on one thing. The flow we perceive is not a direct reflection of the underlying equations, it's a translation. The question is, what are we translating? And how do we know the direction we've chosen is the only one? The next step is to explore what quantum systems might say about this, to look at the smallest changes and the tiniest shifts and ask whether time exists at that level. At the quantum level, the rules are different, not because they're mysterious, but because they operate on scales that don't line up with everyday experience. Things don't happen in neat sequences. They don't even always happen in specific locations. Instead, particles exist in states of probability and combinations of possibilities that collapse only when measured. And in that space of uncertainty, time starts to look different too. In classical physics, an object's path can be tracked continuously. You can watch it move moment by moment from one point to another, but quantum particles don't follow those kinds of paths. They don't move through space and time in smooth, predictable lines. Their behavior is described by wave functions, mathematical objects that tell you where the particle might be and with what likelihood. Until you look, there's no definite position. There's just a spread of probabilities. So what does it mean to say time passes for something that doesn't have a position or a trajectory? In quantum mechanics, time still appears in the equations, but it's different from other quantities. Position, energy, momentum, these are operators. They act on the wave function. But time is treated as a parameter. It's not an observable. You don't measure it directly. You use it to track how the wave function evolves. That difference matters. It means time in quantum theory isn't something you can extract from the system alone. It's something imposed from outside, something that organizes the evolution but doesn't arise from within it. That raises a quiet but important question. What happens if there is no external time to use? In quantum gravity, where you try to unify quantum theory with general relativity, this becomes a serious problem. General relativity treats time as part of the fabric. Quantum theory treats it as a background. You can't easily fit both approaches together. When physicists try, they often run into what's called the problem of time. In the Wheeler-DeWitt equation, one attempt to describe the quantum state of the entire universe, time vanishes completely. The equation describes a static wave function. No ticking, no progression, just all possible states of the universe laid out at once. It's sometimes called a frozen formalism. So how do we reconcile that with the world we see, where events clearly do unfold? One answer is that time might not be global, it might be relational, something that exists only when comparing different parts of a system. In that view, if you have two interacting subsystems, one can serve as a kind of clock for the other. Time then becomes local, internal, not something the universe carries around in its pocket, but something that emerges when enough relationships are in play. These internal clocks are sometimes called quantum clocks. They aren't built from gears or springs, they're systems that undergo predictable evolution, an atom cycling between energy levels, a particle moving through discrete states. When you use one part of the system to define a sequence, you can use it to time the rest. But these clocks are only meaningful if the changes they track are distinguishable, if there's enough structure to support comparison. At the smaller scales, that structure becomes fuzzy. Quantum fluctuations mean that energy levels jitter, space itself might be uncertain, and the closer you get to the Planck scale, about 10 or so 35 meters, the more uncertain everything becomes. Not just the positions of particles, but the shape of space-time itself. In some approaches, space-time is not a smooth fabric, but a network, a web of connections that can shift and rearrange. Time, in that context, is not a continuous line. It's a bookkeeping tool, a way to order the updates in the network. That's where hidden clocks come in. They aren't ticking in the way a watch does. They're embedded in the transitions between states, in the likelihoods that one configuration leads to another. You can't see them directly, but they're there in the structure. Like the quiet rhythm behind a piece of music, not played out loud but guiding the whole shape. Some theorists suggest that if you knew the full state of the universe, every quantum field, every probability amplitude, you could, in principle, define time from within. Not as an external line, but as a measure of how distinguishable the current state is from the last. In that sense, time would be information. It would be the amount of change, the degree of difference, not something flowing, but something measured by what has shifted. That makes time fragile. At very small scales, or in very simple systems, you might not have enough difference to define it. You might get stuck in a moment with no contrast, no arrow, no unfolding. But once complexity rises, once systems become entangled, once energy spreads and patterns form, then internal clocks appear. They don't tick in unison. They don't always point in the same direction, but they give structure. They let parts of the system refer to each other, and from that mutual reference, time begins to emerge. It's not universal, it's not always smooth, but it's enough to create experience. That may be what happened in the early universe. Before there were stars or atoms or anything large enough to carry memory, there may have been only quantum systems, small, uncertain, scattered. But over time, or whatever process resembled time, those systems formed structure, patterns, fields, and with that, the first clocks. Not clocks we could recognize, not mechanical, not digital, but hidden reference frames embedded in the quantum fabric, slowly giving rise to larger, more stable kinds of time. This isn't just speculation. Modern atomic clocks, the most precise tools we have for measuring time, depend on quantum transitions. They use the energy difference between two states in an atom to define a second. That's a quantum clock. Small, consistent, fragile, and remarkably accurate. The fact that time, as we measure it, depends on these systems suggests something deep. That time is not something laid over the universe. It is drawn from it. Not painted on, but pulled out. It also means that if the quantum structure had been different, if the laws or constants had changed slightly, then our clocks might not work at all. Time might not appear. The universe could still exist, but nothing would happen. No events, no unfolding, just a silent wave function, frozen in place. But that's not what we got. We live in a universe full of motion, full of clocks, large and small, full of sequences, shifts and measurements. From the tiniest transitions in a cesium atom to the spiraling of galaxies across space, time appears everywhere. Not as an object, but as a pattern. A kind of shared whisper, guiding systems from one state to the next. What those whispers add up to is the time we live in. But if that time can emerge, it can also be lost. The next question is what happens when time disappears again, not by ending, but by collapsing. If time depends on change and change depends on matter, then it's natural to ask what happens when matter is gone. Not transformed or rearranged, just absent. No particles, no mass, no structures, just fields, or maybe nothing but geometry itself. Can time still exist in a universe that contains no matter? To get there, it helps to look at why matter matters in the first place. Matter anchors clocks. It provides reference points, particles oscillating, systems decaying, fields shifting. Without matter, many of the ways we measure time disappear, but that doesn't automatically mean time stops. It just means it stops being measured in familiar ways. In physics, you can still write equations that evolve over time even in an empty universe. A vacuum solution of general relativity, no matter, no energy, just curvature, still contains a time parameter. The shape of space-time can evolve, not because something is moving through it, but because the geometry itself can stretch or shrink or shift in response to the rules. So in that sense, time exists mathematically. It's built into the structure. You can calculate how space behaves, even if there's nothing in it. But that kind of time is abstract. It doesn't attach to events. There are no interactions, no thermodynamics, no clocks. You can evolve the solution forward and backward, but nothing changes that you could experience. It's like running a simulation with no objects. The grid updates, but there's nothing in the grid. Still, geometry is something. It defines what could happen if something were present. It shapes the way particles would move if they existed. In that way, time in a matterless universe is potential. Not in the philosophical sense, but in the structural one. The scaffolding is there, even if it's not being used. In quantum theory, the absence of matter becomes even more complex. A vacuum isn't truly empty. It buzzes with quantum fluctuations. Fields remain. Particles appear and disappear in brief flashes. Even in the lowest energy state, you get a kind of jitter, a restless base layer of reality. That jitter is sometimes treated as real, sometimes as virtual, But in either case, it suggests that total emptiness may not be physically achievable. So maybe the concept of a universe with no matter at all is only an approximation. Maybe there's always something. But we can still ask what happens as matter becomes increasingly irrelevant, as density drops, as interactions fade, as the structure begins to flatten. Black hole evaporation gives us a window into this idea. When a black hole radiates away its mass through Hawking radiation, the region around it becomes less curved. As matter disappears, the surrounding space-time becomes smoother, emptier. But time doesn't stop. It stretches. It slows near the horizon, speeds up outside, but it continues. In some models, when the last particle is gone and the last wave of radiation has passed, the universe enters what's called a heat death, a state of maximum entropy. No gradients, no usable energy, no reactions, no complexity. In that state, time still exists mathematically. The equations still evolve, but there's nothing happening. No change, no difference, just endless uniformity. That's not the same as a frozen universe. It's a universe where change has no direction, no driver, no structure to carry it. The clocks still tick if any are left, but they all read the same thing. Nothing. No events, no memories. Just the steady spread of sameness. Does time still mean anything there? That depends on what you think time is. If it's just a parameter in the equations, then yes, it's still running. But if time is something that requires measurement, memory, or contrast, then maybe not. Maybe a universe without matter is also a universe without time in any usable sense. One way to test this idea is to imagine a region of space with zero matter, but with fields. A gravitational wave, for example, passing through the vacuum. That wave carries energy, but no mass. It can stretch and squeeze space-time. You could, in theory, build a detector made of matter that measures those distortions. The wave arrives, the detector moves. Time is marked. But remove the detector, and the wave is just a ripple in geometry. It has structure, but no one to measure it. It moves through space, but only in the mathematical sense. You'd still say the wave propagates. You'd still write the equations. But the reality of time becomes more abstract again, not absent, but detached. That shows the dependence time has on matter, not for its existence, but for its expression. Without matter, time doesn't stop, but it stops being useful. The situation gets even more delicate when you consider the early universe. For a brief moment after the Big Bang, there may have been no stable particles, just energy and fields rapidly expanding. Time in that phase is definable, but only by reference to how the fields change. Once matter condenses out of that energy, clocks can be built. Time becomes more concrete, more measurable. So we see time without matter in both extremes, the earliest moments and the far future. And in both cases, it becomes harder to define. Not impossible, but blurry. Time continues to exist as long as the structure of space-time persists, but the sharpness of that time, the way it ticks forward, depends on the presence of matter to trace it. That doesn't make time dependent on matter in a strict sense, but it makes our understanding of time harder to separate from the systems that measure it. And that loops back to experience. You are made of matter. You carry clocks in your cells, in your heartbeat, in your attention. Without those clocks, time becomes a theory. Still real, still present in the math, but unreachable. A kind of background silence. So in the end, the question isn't just whether time exists without matter. It's whether that kind of time is something we can ever touch, or feel, or describe from the inside. Because if time can exist without matter, then we may not be its central story. We may just be one way the universe gives it shape. And if that's true, the next step is to ask whether time needs a universe at all, whether time itself can exist on its own. It's easy to assume that time is a part of every equation in physics, that whatever we're studying, from particles to planets, must evolve through time. But when you step into the deepest levels of the math, something unexpected happens. Time disappears, not in a dramatic way, not erased, just omitted. Some of the most fundamental equations in theoretical physics don't include time at all. They describe the entire universe, all its possible configurations, without assigning a specific clock to any of them. The state just is. It doesn't move, because there's no before and no after. There's no reference for sequence. One of the clearest examples of this is the Wheeler-DeWitt equation. It's a central piece of quantum gravity, a framework that tries to merge general relativity with quantum mechanics. In that equation, time doesn't appear, not because it's been hidden, but because it isn't required. The equation describes the total wave function of the universe, a single, all-encompassing object that contains every possible configuration of space and matter, and that wave function doesn't evolve in time, it just exists. This is often called the frozen formalism of quantum cosmology. It suggests that the universe, at the most fundamental level, is static. All the motion we experience, the passage of time, the rise and fall of stars, the thoughts moving through your mind, is not a result of time flowing, but of structure already embedded in the total state. You might imagine this as a landscape. Every possible configuration of the universe is a point in that landscape. The wave function tells you how likely each point is. There's no direction across it, no path, no ticking, just the terrain. And yet, from certain parts of that terrain, time seems to emerge. Not universally, not all at once, but locally, in regions where certain variables behave in regular ways. You can use one part of the system as a clock, and then describe how the rest evolves relative to it. This is called internal time. It's not a time imposed from outside. It's a pattern that arises within the system. From inside those parts of the wave function, the universe seems to move. But that motion is relative. It's a story built from correlations, not a march forward, but a structure seen one slice at a time. And in that sense, time becomes something like perspective. It's not in the equation because the equation doesn't pick a perspective. It describes everything at once. Only when a subsystem is isolated, when you look at just one part from just one angle, does time begin to mean something. It's not built into the laws, it's built into the way we experience the outcomes of those laws. This isn't just a quirk of quantum gravity. Even in ordinary quantum mechanics, the Schrödinger equation describes how a system evolves over time, but that time is something we input. It's not an operator, it's a label. The system doesn't know time is passing. We do, and in relativity the situation is even more flexible. Each observer experiences time differently depending on motion and gravity. There's no single, global now. There's no master clock. Time stretches and bends with the geometry. So when you step back far enough, when you try to write equations that describe everything, not from within the system but from outside it, time begins to vanish. Not because it's false, but because it doesn't apply in the same way. It doesn't belong to the total state. That's one reason why time might not be fundamental. It's not that we can't describe it. It's that we can describe everything without needing it to start with. The emergence of time, then, becomes a question of structure. What arrangements of matter and fields give rise to something that behaves like a clock? What subsystems can be isolated in a way that lets them serve as reference points? In that view, the flow of time is not a river moving past us. It's a thread we follow through a vast, timeless space of possibilities. The thread isn't picked by the laws. It's picked by the configuration of the system, by the structure of the correlations, and by the conditions we start from. You're not watching time pass. You're watching yourself move through a series of distinguishable states. The math doesn't need time, but you do, because you don't experience the whole wave function. You experience one path through it, one version, one unfolding of structure, and because you remember the past and not the future, you assign direction to that path. That direction becomes the arrow, but the arrow, like the path, is not part of the equation. It's part of the way we read it. So when equations forget time, they're not broken, they're just complete. They describe the full set of possibilities, not as they unfold, but as they exist all at once. It's only when we isolate parts of that set and look at how one part changes relative to another that time begins to reappear. That means time as we know it is conditional. It depends on separation, on asymmetry, on the ability to compare. And if those conditions disappear, time disappears with them. That's not just an idea about beginnings. It's also about endings. Because if time can emerge, it can dissolve. And if it can dissolve, then we have to ask what it leaves behind. You experience time as moving in one direction, from past to future, never in reverse. It seems obvious. You remember what has happened. You can't remember what hasn't. Broken things stay broken. Ice melts but doesn't unmelt. The sun sets, but it never rises in rewind. That direction, the arrow of time, feels built in. But in the deepest laws of physics, the arrow isn't there. At the level of atoms, the fundamental equations are mostly symmetric. They work the same whether time moves forward or backward. If you flip the direction, the math still holds. A particle bouncing off another behaves the same way whether it's running forward or in reverse. There's no preference, no bias. So why does time feel like it has a direction? The most widely accepted answer is entropy, the measure of disorder in a system. As entropy increases, systems become more mixed, more random, more evenly spread. It's not a law that things must become disordered, it's a tendency. There are simply more ways for a system to be disordered than ordered. More combinations of molecules that count as warm air than as a cube of ice. Entropy gives time its arrow not because time flows that way, but because the universe started out in a state of very low entropy. That starting point, incredibly smooth, incredibly structured, left a slope. And everything since then has been falling down that slope statistically. That fall is what we experience as forward, not because time is pushing us, but because that's the direction where complexity tends to grow, where memory forms, where systems evolve into new states that are more probable than the last. You don't see smoke reassemble into a matchstick because it's one of the least probable arrangements of particles in that system. Not because it's forbidden, just because it's vanishingly unlikely. But this means the arrow isn't fundamental. It's a reflection of boundary conditions, the starting state of the universe. If the universe had begun in maximum entropy, there would be no arrow. Everything would already be mixed. No patterns would form. Nothing would happen. Not because change was impossible, but because there would be no measurable difference between one state and the next. No structure to evolve. No direction to follow. That's why entropy isn't just a technical idea. It's the reason clocks move forward. It's the reason you can recall yesterday, but not tomorrow. Not because time forces memory to work that way, but because memory is a structure that depends on increasing complexity. Your brain can store information because it's part of an entropic system, constantly moving toward disorder but using energy to create temporary order along the way. That temporary order is what gives rise to the feeling of now, of then, of next. And it's fragile. You can disrupt it with sleep, with trauma, with illness. The arrow doesn't vanish, but your experience of it shifts. That's another hint. Time as we feel it is not the same as time in the equations. It's shaped by the systems we use to perceive it. That perception may be deeply rooted. Some physicists and philosophers argue that consciousness is only possible in systems that exist inside an arrow, that in order to experience anything, a system must have a history, a way of encoding the past and responding to it. If that's true, then the arrow isn't just part of how we observe time, it's part of why we're able to observe it at all. But even then, the arrow remains an illusion in the strictest sense. Not false, but emergent. Not a property of the laws, but of the conditions. There are thought experiments that push this further. Imagine a system in perfect equilibrium. No gradients, no net energy flow. All parts are the same temperature. In that system, time still exists in theory, but nothing changes. There's no arrow, no reason to say one moment is after another. Now imagine that inside that equilibrium a fluctuation occurs, a small, local drop in entropy. It's rare, but not forbidden. That drop could create a temporary arrow, a pocket where time appears to move forward, where structure arises, where complexity grows, but eventually it fades, entropy takes over, the pocket dissolves. In that case, time has a direction, but only locally, temporarily. It's not built in, it's a side effect. And if you lived inside that pocket, you might never know it had an end. Some cosmological models suggest the entire universe is such a fluctuation, a rare, enormous low-entropy condition that gave rise to everything we see. If that's true, then the arrow is not a cosmic law. It's a story playing out within a larger, timeless context, a brief chapter in a much longer book that doesn't have a clear beginning or end, and that changes what time is. It's not a force, not a flow, it's a perspective, a way of organizing transitions. The direction we call forward is just the direction where entropy increases, but from the perspective of the underlying equations, all moments exist equally. Nothing is singled out. There is no past, no future, just a vast configuration of all states, sitting quietly in their relationships, and we, embedded in one tiny part of that structure, assign direction because we can only see a sliver at a time. It's like walking through a painting with a flashlight. You light up one section, then the next, and from that limited view you create a timeline. But the painting doesn't change. It doesn't move. It contains everything at once. You do the moving, and in that movement the arrow appears. So the illusion isn't that change is happening, it's that the direction of that change is somehow built into the universe. It's not. It's built into us. The next question is what happens when that direction breaks? When time no longer leads to difference? It's easy to talk about time beginning. We imagine a point, a spark, a shift from nothing to something. But when we ask what happens when time stops, the idea becomes harder to hold. It's not just the end of a process, it's the loss of process itself. To begin thinking about it, you first have to separate two ideas: time as a parameter in equations, and time as something experienced through change. Because when time stops, it usually means change has ceased. No events, no motion, no unfolding of states. But that doesn't always mean the parameter disappears. In some physical systems, time continues in the background, even when the system has reached equilibrium. Think of a gas in a sealed container. At first, molecules bounce and mix, entropy increases, patterns form, but eventually everything evens out. The system reaches maximum entropy. No more gradients, no net change. Mathematically, time still exists. You can still assign a later value to the system, but nothing is different. Every frame is the same. From the inside, there's no reference for change. It's as if time, while still present in name, has stopped functioning. That's one version of time stopping, not because the universe breaks, but because it runs out of contrast. In cosmology, this appears in theories of heat death, the idea that the universe, after an extremely long expansion, could reach a state of complete thermodynamic equilibrium. No stars, no black holes, no matter forming or interacting, just low-energy particles drifting through space, too far apart to do anything. In that state, time becomes meaningless, not because the clock is broken, but because no one is left to read it. No changes occur that could be used to define intervals. You can still label slices of space-time, but they're all identical. There's nothing to compare. Another version appears in black holes. As you approach the event horizon, the point beyond which not even light escapes, time slows relative to an outside observer. From your perspective, time continues normally, but to someone watching from a safe distance, your clock appears to slow, then freeze. At the exact edge, time appears to stop completely. That's not because time has ended, but because the geometry of space-time distorts. The curvature becomes so extreme that the path through time changes shape. Your timeline becomes infinitely stretched. From far away, nothing seems to cross the horizon. But for the object falling in, the process continues. This shows how stopping can be relative. It depends on perspective, on frame, on curvature. What looks like the end of time to one observer is just a distortion to another. Then there are cases where the idea of time simply doesn't apply. In the quantum description of the entire universe, the wave function of everything, time disappears from the equations. As discussed before, there is no next, just all possible configurations existing as one solution. No beginning, no unfolding, no ending. In that picture, asking what happens when time stops might be the wrong kind of question. You're asking about a shift in something that doesn't exist in the first place. You're trying to locate a break in a structure that contains no movement. From within our perspective, though, the idea still matters. If the universe runs out of change, if entropy reaches a peak, if temperature evens out, if particles stop interacting, then experience stops. Not because time has ceased in the equations, but because nothing distinguishes one moment from the next. No contrast means no measurement. No structure means no memory. And if you have no memory, you have no way to define time at all. That's what happens in certain mind states too. Under anesthesia, in deep sleep, or in states of neurological disruption, your brain can stop encoding change. You wake up and find time missing, not because it stopped, but because you weren't present for its unfolding. That's the lived version of time stopping, a gap with no internal sequence, no edge, no motion, just an absence. So when people ask what happens when time ends, they often mean, what would it be like? And the answer is probably nothing. Not in a dramatic way, not as an erasure, just nothing to track. No unfolding, no before, no after, no events to string together, not even stillness, because stillness is only meaningful against the background of motion. In such a case, time doesn't stop with a line. It fades, it becomes undefined. That's the critical difference. Time doesn't require things to end, it just needs things to change. Without change, it loses its grip. Without matter, or entropy, or observers, or clocks, it dissolves. Not violently, but by becoming irrelevant. The equations still allow for slices, for labeling, for sequencing. But none of those slices carry content. None of them differ. It's the difference that defines time. Without it, the labels are just placeholders. So what happens when time stops? If you mean physically, when there are no more changes, then the system becomes static, uniform, undisturbed. If you mean experientially, when memory, contrast and structure are gone, then there's nothing to perceive, nothing to report, not even a sense of waiting. From the inside, that might not feel like anything at all, and that opens up a final possibility, that the end of time isn't an edge. It's just a kind of quiet, where nothing new occurs, no distinction, no measure, a place beyond the arrow, beyond the clock. But the universe doesn't stop because we reach that place. It simply becomes silent. Whether that silence lasts a second, a trillion years, or an infinite duration, no one would know. And in that silence, the story of time, as we know it, concludes. But there's still more to ask. Because if time can stop, then so can the universe. And if the universe stops, or ends, what happens to time after that? If the universe ends, does time go with it? Or could something remain, a kind of afterstate, quiet and unchanging, but still structured in a way that includes time? To approach that question, you first have to ask what kind of ending you're imagining. There are several possibilities, each with different consequences for time. In one, the universe expands forever, galaxies drift apart, stars burn out, black holes evaporate. Eventually, all matter decays. What's left is a thin, cold spread of particles slowly stretching into emptiness. That's known as heat death. It's not an explosion or a collapse. It's a fading. No energy gradients, no structure, no usable information. In that version of the ending, time continues. The equations still describe expansion. The metric of space keeps stretching. But for all practical purposes, nothing happens. No events, no observers, no clocks. Time becomes disconnected from experience. It's there, but silent. Another version is the Big Rip. In that model, the acceleration of the universe's expansion grows so extreme that it eventually tears apart galaxies, stars, planets, even atoms. The fabric of space stretches so violently that everything loses coherence. Not just structure, but even the rules that define structure. In that scenario, there may come a point where space-time itself no longer behaves in a predictable way. Equations fail, descriptions stop working. Time, if it still exists, becomes impossible to trace, and beyond that point it may not be meaningful to speak of duration at all. Then there's the big crunch, a reversal. Expansion slows, then stops, then contracts. All matter pulled back together by gravity. Galaxies collapse, temperatures rise, density increases until the entire universe folds back into a single point, a mirror image of the Big Bang. Here, time doesn't vanish. It reverses in structure, but not in direction. Events still unfold, just toward increasing density instead of dispersion. The sequence remains, even if its shape changes. What happens at the singularity, the final moment of collapse, is unknown. It might mark the end of space-time, or the beginning of something else. In certain cyclic models, that collapse triggers a new expansion, a bounce. The end becomes the start of the next universe. If that's the case, then time doesn't end, it reboots. But not necessarily in a way that preserves memory or history. A timeline, not a continuation, but a replacement. And finally, there's vacuum decay, a quantum possibility where the universe is not in its true lowest energy state. Instead, it exists in a false vacuum, a temporary configuration that could tunnel into a more stable one. If that happened, a bubble of a lower energy reality would form and expand at the speed of light, altering the fundamental constants and laws inside it. To anything caught in its path, the transition would be instant. No time to respond, no time to process, just a sudden shift into non-survival. Inside that new region, time might still exist, but it would not be our time, not our physics. Possibly not any meaningful structure at all. These scenarios all offer different versions of the end. Some are gradual, some are abrupt. Some leave time intact but unusable. Others dissolve the structure that time depends on. What they all have in common is this: time, as described by physical theories, doesn't necessarily require our presence. It doesn't stop just because we're not there to measure it. It continues to be part of the structure, at least in the equations. But if time continues in a universe where nothing happens, no observers exist, and no systems change, then what is that time really doing? Is it still a dimension, or has it become a label without meaning? In many of these end-stage scenarios, the universe becomes so uniform, so uneventful, that time becomes impossible to detect, not because it isn't there, but because there's nothing to compare. No difference between one slice and the next. The metric stretches, but the structure doesn't update. You can still number the moments, but you can't tell them apart. It's like writing dates on blank pages. They move forward, but the content never changes. That might be the closest thing to a post-time reality. Not an end of time, but a state beyond its use. No clocks, no systems, no change. A background that can't be measured because there's nothing left to do the measuring. Still, even in that quiet state, time could persist as part of the underlying structure. Just not as something active, not as flow, just as a coordinate, one that no longer has anything attached to it. Alternatively, it's possible that once all meaningful structure ends, time stops being relevant not just practically, but fundamentally. That the concept itself breaks down. That without matter, motion, contrast, or energy, there's no longer a need for time in any form. Not in experience, not in theory, not in math. If the universe ends not just in content but in rule, if the final state is not empty but undefined, then time, like everything else, may dissolve. Not erased, just no longer part of the description. In that view, the end of time is not a wall. It's a fade-out, a tapering of what time can do, a gradual collapse of distinction until there's nothing left to separate one moment from another. And what remains? That depends on whether time is a frame or a function. If it's a frame, it might remain even without use. If it's a function, something built from difference, then once difference disappears, so does time. That leaves one more question. If the universe ends and time along with it, where does that leave us? Not physically, but personally. What is time to you once there's no universe to contain it? If all external clocks were to stop, if the universe grew quiet and flat and no more events ever occurred, would time still exist? And if it did, would it exist only in the place where the last comparison remains, your mind? Memory, more than almost anything else, shapes your sense of time, not because it stores the past, but because it constructs a way to move through it. Without memory, there is no sequence, no link between one state and the next. You might see motion, hear sounds, feel changes, but they would pass through you without context. Experience would collapse into isolated frames, disconnected from one another. Memory holds time together by creating continuity. You don't just remember facts, you remember order. You know what happened first, what followed, what came after that. The structure you build from those relationships is what gives you a sense of narrative, a before, a now, and a later. That sense isn't drawn from the equations of the universe, it's drawn from patterns in the brain. In that way, memory doesn't just help you track time, it may be the thing creating your personal version of it. Neurologically, memory is built from change. When you experience something new, certain patterns in your brain are altered. Neurons adjust, connections are reinforced or weakened, activity is stored. Over time, these traces allow your brain to reconstruct parts of the past. Not perfectly, but with enough detail to hold a shape. That shape is where your experience of time lives. The reason you feel that time is flowing may not be because it is flowing, but because your memory constantly updates. The present moment doesn't just stand alone, it's compared to a series of recent states. That comparison creates motion, not in the outside world, but in awareness. Some studies suggest that this system can be interrupted. Under certain conditions, trauma, sleep, anesthesia, neurological damage, memory can stall. The world keeps changing, but your internal record stops updating. Time continues, but your experience of it drops out. When you come back, you have no sense of how long you were gone. That shows how tightly time is tied to memory, not just as a tool for measurement, but as a requirement for presence. There's also a strange asymmetry in how memory works. You can remember the past, but not the future, even though, in some physical theories, the future is just as fixed as the past. But memory doesn't work by reading stored files from space-time. It works by recording physical traces, effects that happen only after an event occurs. That's why you can't remember something that hasn't happened. Not because it's impossible in principle, but because memory requires a direction of information flow, from change to trace to storage. It's also why you can't remember the same event more than once in a truly identical way. Each act of remembering alters the trace. The very process of calling up the past changes your relationship to it. That means time, as built by memory, is not just a passive sequence, it's an ongoing construction. Even now, as you listen to this, your memory is forming patterns, holding a word, connecting it to the next, building expectation, registering change. All of that is giving you a sense that this moment is happening now and not before. But if memory is the core of time and experience, what happens if there's nothing to remember? In the final state of the universe, a state with no motion, no interaction, no contrast, there would be nothing for memory to store. No inputs, no patterns, no variation. The brain, if it somehow still existed, would receive no signals, no shifts in light, sound, or sensation. Without those, memory stops updating. Awareness shrinks. The idea of now loses shape. And with that, personal time dissolves. So time, at least in experience, is memory dependent. Without records, there's no past. Without projections, there's no future. Without enough structure to compare, the present becomes indistinct. That doesn't mean time isn't real, but it suggests that your version of it, the kind that has weight, direction, meaning, is made not from space or motion, but from remembered change. And that idea reaches even further. It means your sense of self is tied to time. Not just because you exist across moments, but because your memory holds those moments together. You think of yourself as continuous because memory provides the link. You feel the difference between who you were and who you are because that difference is recorded. In some way, the mind becomes a kind of clock, not because it ticks evenly, but because it carries a record of what was. But it's a fragile clock. When memory is disrupted, the sense of time distorts. Moments stretch or collapse. Events lose sequence. The arrow wavers. That reveals how much of what you call time is built from internal structure, not from the cosmos, but from the folds of your own brain. So when we ask if time continues after the universe ends, part of the answer depends on whether there's anyone left to remember it. Because without memory, time loses shape. And without shape, it becomes something else, an unmarked backdrop, not a path. Still, if memory is what gives time meaning, then you may be part of how time becomes real, not just by noticing it, but by holding it. That brings us to one last idea. If time is built through memory, and memory is built through awareness, then perhaps the story of time ends not with the universe, but with you. Throughout all these layers, the equations, the particles, the clocks, the stars, time has looked like something external, a backdrop, a frame we move through. But if you follow it all the way down, if you strip away the tools and the structures and the systems, you come to a strange possibility that maybe time isn't a thing you pass through. Maybe it's something you generate. From the outside, your body is just another physical system, made of atoms, obeying thermodynamics, sitting on a planet that spins. You age because your cells change. You move through time because the world moves around you. But from the inside, the experience is different. You don't just see time, you carry it. You remember what just happened. You anticipate what might come. You measure difference, track sequence, maintain a sense of now that slides invisibly forward. Not in steps, but in awareness. That awareness isn't outside the world, it's part of it. But it isn't reducible to a clock. It doesn't just tick, it assembles. It builds time not from numbers or equations, but from contrast, memory, change, attention. You wake up in the morning and you already know the order of things, not because you checked a timestamp, but because your mind has built a story that unfolds. That story follows an arrow, not a physical one, but a constructed one, a path from one mental state to the next. Each moment your brain receives new information, integrates it, decides what to keep, what to ignore, how to arrange it. In doing that, it defines time, not universally, but personally. No two people feel it the same way. No two memories align exactly. That's not a flaw. That's what it means for time to live inside a person, rather than just around them. And when something changes, when you're ill, or frightened, or focused, time bends. It expands, or tightens. The outside world continues, but your internal measure doesn't always match. That difference is a clue. A signal that what you call time may not be just out there, waiting. It may be here. Your thoughts don't unfold on a timeline. They make one. Your attention doesn't follow time. It shapes the feeling of its motion. Your memories aren't just records. They're the glue that gives direction to a life. So when we ask where time goes when the universe ends, or when matter stops moving, or when clocks break, there's one answer that stays. It goes with you. Because without something to remember, without someone to organize change, time becomes a list without entries, a line without points, still definable, but empty. And if time emerges from difference and difference is perceived through awareness, then time as you know it might be inseparable from consciousness. Not because the universe depends on you, but because your sense of reality depends on time, and your sense of time depends on how you live in it. You are not outside of time, but you're not simply inside it either. You form it, piece by piece, from the way your mind handles the world. And when your thoughts pause, or your memories quiet, or your awareness lets go, time softens. Not because the universe has changed, but because the version of time that mattered most, the one you felt, carried, shaped, has gone still. Maybe time was never a thing on its own. Maybe it was always a relation. a sequence of awareness formed by memory, carried by mind, marked by change. Maybe time is what the world looks like when you're paying attention, and maybe, in the end, time is you. Thank you for sharing this moment. Until next time, may your own time feel slow, deep, and just right.